Hello students and welcome to my channel Maths Hub. So today let's talk about the generating functions. Now let's come to the definition of a generating function. The generating function is for a sequence S with having the terms a0, a1, an of real numbers, it is an infinite sum. That means the generating function is denoted as g of s comma z, where it is an infinite sum of the sequence of these terms, that is a0 plus a1z plus a2 z square plus so on up till a and zn, and the sum is going till infinity. So in the summation form, we can write it as n going from 0 to infinity, a n z raised to power n. Right? So this is the definition of a generating function. So either you can denote it by the word gz or you can denote it as gs comma z. Right? So now let us see that for a particular sequence of terms, what are their generating functions? And then once we get the understanding of generating functions, we will use these generating functions to solve our non-homogeneous recurrence relations. Right? So let us look at the first sequence. We have the first sequence as 1 by n factorial, so we have to find its generating function. So let us see how to do it. Now we know that a generating function g of s comma z, it is nothing but summation n going from 0 to infinity sequence Sn into z raised to power, right? So now we are given that the sequence, the nth term of the sequence is 1 by n factorial. So let us substitute over here into z raised to power n. So now when we put n equal to 1, the first term that we will get is 1 by 0 factorial into z raised to power 0. So that is 1. The second term that we will get is when you put n equal to 1, so it is z upon 1 factorial. Then the next term, it is z square upon 2 factorial, so on. The nth term will be z to the power n by n factorial plus so on, right? So if you remember your basic maths, this is the expansion for e raised to power z, right? That means whenever the sequence is 1 by n factorial, we will get our generating function as e raised to power z, right? So at the end, we will prepare a table where we will write the sequence on the left hand side and we will write its generating function on the right hand side, right? So this is the first example that we have done on generating function. So now let us move on to the next example. So in the next example, we have the sequence of terms as 1, 1, 1, 1, and we need to calculate what is the generating function. So as the generating function g of z is summation n going from 0 to infinity, the sequence, if I denote it by Sn into z raised to power n. So this is summation n going from 0 to infinity. The terms of the sequence are all 1. So the nth term is also going to be 1. So it is 1 into z raised to power n. So when you open up this expansion, we'll get the first term as 1 plus next is z plus z square plus z cube and so on. So now if you remember your binomial expansion, this is 1 upon 1 minus z, right? So this is your expansion when we have the sequence as 1, right? So this is the second entry in our table. So now let us move on to the third example. So here in the third example, we have to calculate the generating function when the sequence is summation, when it is b into a raised to power n. So let us see. So sequence, that is a generating function g of sz, is summation n going from 0 to infinity. It is Sn into z raised to power n. So we are given the value of Bn as Zn as Sn as b into a raised to power n into z raised to power n. So you can see that b is constant. You can remove that. You can take it outside the summation symbol. And we have the summation running on az. We can club it and we can write it as az raised to power n. So now when you open up the bracket, we'll get b times. First term is 1, then we have az, then az square and so on. So you can correlate it with a GP series also. It's a GP series, infinite GP series with first term 1 in common ratio AZ. So you know what is the sum of the infinite terms. So it is 1 upon 1 minus AZ. Right? So the first term that we did was, what was the first sequence that we did? The first sequence was 1, and for that the generating function was 1 upon 1 minus Z. Then the next sequence that we have just done now is b into a raised to power n, and the sequence is b upon 1 minus az, right? And what was the first one that we have done? That was 1 by n factorial, and for that the generating function was coming out to be e raised to power z, right? So now let us move on to the next one. So the next sequence is a, and we need to calculate the generating function for this. So we can see that when it is b into a raised to power n, when the sequence is this, we get the generating function as b upon 1 minus az, right? This was the sequence. So here, what do you find? What is it? You can see that B is playing the role of A in this question here, and A is playing the role of 1, isn't it? Right? So if you substitute these values in this generating function, so what is your generating function going to be? G of SZ. Instead of B, we will get A. Instead of A, we will write 1, right? So we get the generating function is A upon 1 minus Z, right? Okay. And then we have the next one. If our sequence is a raised to power n, so we will just relate it with the same thing. If the sequence Sn is a to the power n, or you can say it is b into a to the power n, then the generating function was b upon 1 minus az. So here you can see that I have substituted b as 1. So if the sequence Sn is a to the power n, then the generating function will become 1 upon 1 minus a, right? So if the sequence is a to the power n, it is 1 upon 1 minus a. Next, if the sequence is now n, so let's try to derive it. So the generating function is GSZ, that is equal to summation n going from 0 to infinity sequence Sn into z raised to power n. So when we substitute the value of Sn, we will get n into z raised to power n, which is, now open up the brackets, when you put n equal to 0, you will get 0. When you put n equal to 1, the first term is z, then we have z square, then we have z cube, and you will also get 2 and 3 along with it, then 4z to the power 4, and so on. So you can see that you can take out z common from all the terms, and we are left with 1 plus 2z plus 3z square plus 4z cube, and so on. So z is common, and this expansion using the binomial, it will become 1 minus z raised to power. So that means when the sequence is simply n, then the generating function is z upon 1 minus z, right? So now we are in a position to prepare the table now. So what is that table? We will write the sequence here, and we will write its generating function. So when we will do the questions on recurrence relations, we need to know for the sequence what are their generating function and vice versa. So the first one was when it is 1 by n factorial, the sequence is e to the power z, generating function. If it is 1, then the generating function is 1 upon 1 minus z. If it is b into a raised to power n, then it is b upon 1 minus az. And you can make corollaries from here that if the sequence is simply a to the power n, it is 1 upon 1 minus az. If it is simply a, constant a, then it will be 1 upon a upon 1 minus z. Right? And then the last one is when the sequence is n, then the generating function will be z upon 1 minus z whole square. Right? So there are almost six sequences for which the generating function should be known to us. Right? So I hope from the sequence you can now develop the generating function. So let us do one more question and let us see that how to identify the sequence when the generating function is given to us. Right? So the generating function g of sz is given to us as 6 minus 29z upon 1 minus 11z plus 30z square. Right? So first of all, if you look at the table of generating function, we need linear terms in our denominator, right? Or we need a whole square in the denominator. So let us try to use the concept of partial fractions and let us try to break it down. So let us try to make the factors of the denominator term. So the factors of this term will become 6 minus 29z upon 1 minus 6z into 1 minus 5z, right? So now let us apply the partial fractions and let us calculate this. This is a upon 1 minus 6z plus b upon 1 minus 5z, right? So let's cross multiply the terms and let us try to calculate the values of a and b. So after your calculations, you'll find that the coefficient a is 7 and the coefficient b is minus 1, right? So we get our generating function as g of s comma z is equal to 7 upon 1 minus 6z minus 1 upon 1 minus 5z, right? So now in the generating table, the table that we have just made in the previous slide, you will see that when the generating function in fact is a upon, or you can see if it is b into a raised to power n, when this is the sequence, the generating function is b upon 1 minus az, right? So here you can compare it. B is 7 and a is 6. So this will become the sequence 7 into 6 raised to power n minus. Now compare this with the right hand side and you will see that b is now 1 and a is 5. So this is 5 raised to power n. That means the given generating function has 7 into 6 to the power n minus 5 to the power n as the sequence, right? So I hope you have understood the topic, how to develop the generating function from the given sequence. And if the generating function is given to us, how to write back the sequence, right? So if you like the video, do hit the like button. And those of you who have not subscribed my channel, do subscribe my channel to get the latest updated video. Believe in yourself and you will be able to achieve. Thank you so much.